This video is going to show you how you can study the dependence of some numerical variable on a categorical variable. So a really nice illustration of this situation is this floor wax problem out of the course packet. Here we have two types of containers. One is made out of plastic, the other one's made out of metal. And we sell them in different stores and observe the sales. And so then the question is, how does the type of material that the packaging is made out of affect our sales? Okay, so I'm going to show you how to do this in R. Let's go over to R. And the first thing we want to do is read in the data. So there happens to be a CSV version of this on my computer. You can get it off Canvas if you want. So it is in, I put it in teach data, and then there's a file called wax.csv. Let's just go look and see what's in there. Now, what you're going to see is that material has been coded, 1 for plastic, 2 for metal, and I'd really like to have some meaningful labels in there. So let's get those in. So what I'm going to do is say wax $material. I'm going to overwrite the original variable as a factor. So let's say wax $material. And then you're going to notice on the bottom here, the next thing I need to do is specify the levels. So I'm just going to say 1 and 2. And then the next thing is the labels. So let's see, the first label is plastic. And then the second label is metal. So now if we do a head on this, you're going to see that plastic and metal appear. All right, so the next thing I want to do is look at my data. We should always look at our data the first thing. So this is going to be your first exposure to a formula. So we're going to use the function called boxplot, and we're going to stick a formula in here. So the format of the formula is the dependent variable is a function of the independent variable. So the dependent variable here is sales. Now in R with a formula you always use the tilde sign, and then you list the independent variable. So we're saying sales is a function of material. Now you have to tell R where to get the data. So the data set, the data equals argument is actually optional. The second one is always the data set is wax. So go look in the wax data frame, and we're going to model sales as a function of material. And this is the box plot you get. So if you've watched the SPSS version of this, the first thing we notice is that there's a big outlier down here, and that makes us a little bit nervous. And in the SPSS video, I went back and I checked to make sure I typed it right, and sure enough, I did type it right. That is 360. So we have a problem with store 2. Not quite sure what's going on with that. And at this point, we're going to kind of proceed with the analysis, but we should probably check and see if there was something wrong in that store. Maybe the shipment was late, maybe it wasn't displayed right or something. And if any of those things happen, that would give us a justification to remove that outlier. In the absence of any sound rationale, let's kind of analyze it both ways and see how robust our findings are to that outlier. Okay, you can kind of stop at well, actually, one more thing. I want to show you how can we get the means and other descriptive statistics broken out by material. Well, I'm going to show you the wonderful part of R. So I'm going to bring up this previous command, and we're going to get rid of boxplot. And I'm going to change this to aggregate, A-G-G-R-E-G-A-T-E. And what we're going to say is, we want to break out sales by material. I'm going to give another argument. This is the function I want to break it out by. So if you say fun, because this is way too much fun, you can say mean. And now we know the mean sales for plastic and metal. And you can stick any function there that you want. So for example, we could put variance, we could put the standard deviation, we could put the min, any function you want, and it's going to break it out, break these figures out by plastic and metal. So we now know the mean sales and so forth. All right, you can stop the video here. I'm going to add another section though to this video. that's going to show how to do F and T tests on this. All right, so to do an F test, we're just going to bring up the previous command, get rid of the fun thing, and what we're going to do is change aggregate to f.test. No, sorry, var.test. And this is going to allow us to evaluate whether or not the variances are equal. So the first thing I want you to note is that up above we computed some variances. So 431, 233. This has actually computed the variances actually as a ratio. So if I just take 431.111 all over 233.1222, whatever, notice I get this is the ratio of the variances. Now, this is testing the null hypothesis that the variances are the same. My p-value, you're going to see, is quite a bit bigger than 5%. Therefore, I cannot reject the null hypothesis that the variances are equal. Equivalently, you could say the ratio of the variances equals 1, because if the ratio is equal to 1, that means the variances are equal. You'll also see that 95% confidence interval covers 1, so we can't rule out 1 as a possible ratio. Therefore, we're going to assume equal variances. Okay, now let's go do the t-test to find out if the means are the same or not. So we're going to bring back that previous command and change var test to t.test. Okay, and ordinarily t-test assumes unequal variances, but we just learned up above that the variances could potentially be equal. So if you say equal.var equals true, that sets the variances equal to being, oops, I always get this wrong. I always get this wrong. It's kind of a confusing command. It's var.equal, not equal.var. All right. Doesn't make much of a difference, to be honest. The p-value is about the same whether you use equal or unequal variances. The point is this. The p-value is substantially bigger than 5%, so we don't have evidence to reject the null hypothesis of equal means. So I don't have any evidence at this point to say that the sales are different, even though on the box plot it sure looked like sales were higher with plastic than with metal. All right. Now let's just pause for a second and remember that we have this outlier. So this outlier is problematic because it inflates the variance of the plastic group, and that's going to make it much more difficult to reject the null hypothesis. It destabilizes the estimate of that mean. So if we wanted to do kind of a robustness check, see how sensitive our results are to having that outlier in the data, what we could do is, let's go back to the var test. And with all modeling functions in R, you can add a subset command. So I'm going to say subset equals, and let's just say store not equal to 2. Now, you're going to see the variances are really not different. I mean, the p-value is very close to 1. The ratio is very close to 1 of the variances. So we don't have any evidence to think that the variances are different. Okay, so I'm going to bring back this command, and let's go add our subset command to this. Subset equals, okay, store not equal to 2. The exclamation point is not. Now, what you're going to see is that it's showing the mean for plastic is a bit higher than the mean for metal. And we have a p-value that's less than 5%, so we can reject the null hypothesis and conclude that there is a difference in the means. So you got to be really careful with outliers, and you need a good justification for dropping them. But what we've seen in this case is that our final conclusion really depends on that outlier. And if there was something wrong, we probably want to get that out of there. Maybe we need to do a bigger test on this. Okay, so that's how you do a box plot. You can break out a numeric variable by a categorical variable with descriptive statistics like the mean and the min and the max and all that I showed you. And then finally, the final polish is to do tests, and they all use this formula command. So that's really important to get to know.